My name is Guillermo Christen. That was a good attempt by saying my name. I'm the CTO of IntentHQ. It's a company that tries to help clients understand their customers better by analyzing activity data, which is why we did this kind of work. And I've given this a subtitle, an unprincipled approach, because what I hope to get in the balance of this talk is an idea of how we went through the application of autoencoders. So what this talk will cover, some deep learning or really neural network prerequisites, just so that we're all on the same page, our motivating problem, why we did any of this work, autoencoders, of course, and then a brief discussion about sparsity and loss functions, and finally, future work. What this talk will not cover is complex mathematics, optimization in detail, though you should have a strong intuition about why neural networks learn, and generative models in detail, though hopefully we do get to have a discussion towards the end about that. So to begin with, we usually start with this. If you're looking at a single layer neural network, this is the traditional notation for it. You'll have some linear transform of x plus a bias that'll produce a value z, and you'll take that and pass it through some activation function, usually some nonlinear activation function. And that'll give you h. And a different representation for this often uses this, right? And that's the neural, in neural networks, the analogy to biology. And it's just an explanation of how you take a particular input and multiply it by a particular row in a weight matrix, sum all of that up, add the bias, and again, pass it through a function. And I usually find it useful to have visual representations of what I'm doing, understanding visually the work that I'm doing. And you can think of that weight matrix just as a matrix, a set of numbers, hopefully close to 0, random, depending on the problem that you're trying to solve. And your training set or your batch as a set of column vectors that if you dot product, you'll get some set of scalar values which you want to pass through those linear activations, nonlinear activations. And in Python, it's straightforward, right? Just do np dot. Take your weight matrix, your samples, and add that bias. And finally, just pass it through that function, right? A rectified linear unit, or a hyperbolic tangent, or a sigmoid. So squishing the value, usually, or constraining it in some way, in the case of a linear activation. And I've always found it useful to think of each row in that weight matrix sort of as a template. So in the linear case, each row ends up being a template on how to deal with the different dimensions of your input. And if I was thinking about doing this in MXNet, which is part of what this talk is about, I would do it in the following way. I'd just import the MXNet library, define a variable for my input, define a variable for my weights, define a variable for my bias, do the dot product, do the addition, and then pass it through an activation function. MXNet provides a bunch of different APIs, and I'm going to be using the symbolic API. But you can see how here we're essentially sort of building a symbolic graph, a graph of computation. And I've added this little bit at the end. You can create an executor using a simple bind mechanic and a context. I'll talk about the context later. But that executor is quite useful because before you've done anything, you haven't executed any programs, you're just building your architecture, you can start introspecting that architecture. Do the shapes match? Are you doing things the way that you're supposed to? Do your dimensions work? And that's pretty useful so that you avoid time later fixing problems. A different way to do this, slightly shorter, simpler way to do this is choosing the fully connected layer. And the fully connected layer is sort of like the dense layer in other frameworks. And you just have to pass the number of hidden units that you'd like to that fully connected layer and then back onto that activation. So far so good. This should be basic neural network stuff. Great. All of this really is to say, if this was a single layer neural network, your prediction y hat would be given by primarily your W, right? Most of your model is in that W. Though, of course, there's a bias, and it does go through a nonlinear transform. But why does that matter? Well, in the context of neural networks, really in the context of any optimization problem, you're trying to find the difference between what you predicted and what was true, whether that's in unsupervised and you're comparing the same thing or in the supervised setting. And that's with respect to your parameters, right? So you have some cost function J with respect to W and to B, and you want to find which Ws and Bs meet the criteria or find the solution, right? And really that's just the process of moving the values in W and the values in B so that you get to the point that you're interested in. And that's really just traversing the surface of a loss function. There was a great talk yesterday about, or the day before yesterday, about following the gradient. this should tell you a lot. This should give you an intuition about the importance of your loss function, right? So it has to be, of course, differentiable, but its surface will determine how easy it is to actually end up solving your problem. And usually we'll solve it with some version of stochastic gradient descent, some set of steps that we take. In fact, here the jagged lines represent the fact that we're using batches and not the full data set. And so we sort of oscillate through this surface until we find the solution, if we converge, of course. Something that I've found useful in the past, too, is to think about what you're doing. Imagine that the function that you're trying to solve is just explicit. And in most frameworks, that explicit function ends up being a computation graph, and that's just a very simple computation graph. You have, in this case, W1 times W2 plus B. And you can imagine how that computation graph ends up acquiring some values that you propagate forward. Why does that matter? Well, I found this a useful intuition because you can easily see from a description like this one how backpropagation would work, right? So if you wanted to find the partial derivative of each of these interim steps, this is sort of the intuition of the chain rule, right? You just go back one step, and go back one step, and go back one step. Okay, so our problem. Why are we looking at autoencoders? Now they have a little bit of background on neural networks. We're looking at autoencoders because of the data that we handle. In particular, because it's a very sparse, very large data set. And in particular, we're looking at a very highly dimensional space. So our vocabulary is millions of potential actions. Even though it's a very large data set, as in we get millions and millions of samples, it is very sparse and also very variable. So the mean number of actions that a customer that we're analyzing takes, so a customer that we're analyzing on behalf of a client per week is 4.1, and the mean number of actions per day is 1.8. So what does that mean? There's a bunch of problems. One, with dealing with that amount of data, millions of records in this very high dimensional space. There's also a number of problems in trying to figure out how to get the meaningful structure from that data. Of course, there's also the problem of this being discrete data. These are counts of action types. Think of an action type as maybe somebody visited a support website or got a certain support SMS. Right? That's an action type, and I count the number of times that those happen. Those exist in a discrete space. There's also multiple downstream modeling tasks that we'd like to be able to do after we process this data. In the context of telecoms and often other industries that have this form of data, you won't use behavioral data almost at all because it's so unwieldy. And when you do use it, you use it in very specific cases. So you take your 8 million plus vocabulary and you look at a single action type because you care about that. And you can't do that over and over again, especially if you have constraints in time and resources for each iteration. There's a big engineering problem there, and we're trying to solve a little bit of that. But there's also, of course, a data science problem there. So what do we want? We want a transformation from a discrete space to a continuous space. We'd like a representation that is smaller and easier to use. Just from a data engineering perspective, it's easier to handle, less subject to memory constraints. We'd also like to make sure that we find that embedding, so that representation has properties that are useful in downstream modeling tasks. And that's a pretty key part. So we must retain the information while also keeping within the representation the characteristics that will be useful later. And in particular, for our case, we'd like to make sure that that representation keeps characteristics that are useful in modeling sequences. So you can think of a piece of data as a time unit, a day, a week, a month. And in a way, you can think of it, say, as this. You get a particular customer service domain access to a particular SMS sent, and we'll take that piece of data, very sparse count, and we'll start modeling over it. And each of these, we'll look at this visual representation later. Each of these we'll attempt to compress these so that we can use them later. And of course, we didn't go for autoencoders first. Any data science problem that you have, go for the simplest version first, and then try the next thing. And the first thing that we tried, of course, was matrix factorization. We tried a bunch of different types of matrix factorization, and we ended up arriving at the conclusion that though we were able to compress the space in a meaningful way, right? We were able to find some principal factors, if you will. The reconstruction, our ability to compress that space, was really limited by the ability to keep rare information. So in the end, if we chose a large number of factors in our compression, then it was almost linear the benefit that we got on rare domains. To be much clearer, it was the same if we just kept the most popular domains by count and didn't do any most popular domains, most popular actions, and didn't do any compression. This is important because rare actions are often the ones that you care about, and this is past removing things that are very popular and normalizing. So if I take an idea of autoencoders, what we're trying to do is find an embedding, and we can start with this definition. So you have some function that takes some input x and gives you an encoding, and then some function that takes that encoding and gives you a deconstructed version of x, right? And so the loss would be x itself and g of f of x, right? And a simpler way to think about this is you have some data set, you're trying to find this small latent representation that's able to reproduce the data set with the best fidelity, if you will. In this case, we're talking about an under-complete autoencoder. And an under-complete autoencoder is just one where the bottleneck, the space that you're trying to compress to, is smaller than the original input dimensions. And you can have over-complete autoencoders, where the bottleneck, in fact, isn't a bottleneck, right? It's an expansion. And over-complete autoencoders, just on their own, make no sense. But you can do some things to make sure that the over-complete representation gives you useful properties. For example, adding noise. And some of you might have looked at denoising autoencoders in that context. This can be used for things that you've probably seen in the web, reconstructing images or reconstructing sound waves, or also reconstructing certain types of discrete data like the one that we're dealing with. And an intuition for this, a simple intuition for this is if I asked you to do that. If I asked you to remember that sentence and just choose 2 words to remember it, you'd probably think of something like blue and sentence, or I don't know what you choose, but that's the idea. You're compressing the space, right? You only have 2 words. Slightly more in detail, that encoded representation, if you go back to the original neural network description that we gave, right, the single layer, it's almost the same, right? So we have some weights, 1 multiplied by x plus a bias, and that gives you the encoder, and then the decoder. You can have tied weights. In the case of tied weights, each layer essentially shares the weight matrix. In that case, W2 would end up being really just a transpose of W1. And that's useful in certain scenarios where you want to force constraints. We are not using tied weights, and we don't need to apply that constraint. But if I was looking at this in MXNet, because it's part of what I would hopefully like you to get out of the talk, it would sort of look like this. I have some set of layers that I'm defining, and by layers I mean the input dimensions of each layer, and then some method that builds a stack, right? So it builds either the left-hand side or the right-hand side, the encoder or the decoder. And I'm passing the original data, I'm passing the layers, I'm passing the activations that I'd like to use, and the prefix. So in the encoder, I'm passing the actual data, right? And to the decoder, I'm passing the encoder, that is the symbol that represents the encoded representation. In a bit more detail, you could think of build stack as something like this. Just take a set of layers, enumerate through the layers, create the linear transform, so the fully connected layer. If there's an activation, add the activation. So simple, hopefully straightforward. So for us, that meant this was our first reasonable pass. And we did a little bit of work to get there, but it just meant that we had 2 layers on one side, 2 layers on the other side, 200 dimensions for our embedded representation. And I'm giving a hint as to how I'm comparing things, but I'll go over that in a little bit. We also centralized, of course, all the model creation into a class called Auto-encoder model, but you can find a ton of that on the web anyways. And there's a hint there to the contexts thing that I mentioned earlier. So when we did the simple bind on the executor, you could pass a context, and we had passed the CPU. In MXNet, you can pass GPUs to your model. For the most part, MXNet will handle how to distribute that data into each particular GPU, though you and your functions can also define how and when to copy data from one GPU to another, which is quite useful. So before I get into this, it was just defining how you'd start defining that class of a model, a little discussion on MXNet. So why MXNet and not TensorFlow or Keras? So before, MXNet really meant that you wanted to go a little bit more low level, but you got speed benefits. So MXNet, I still think, beats the other frameworks in the speed benchmark. Now, there really isn't a reason, in my opinion, not to choose it, because with their new Gluon API, it is really a very simple mechanic to build networks. Having said that, I would encourage you to use the symbolic API because it really makes you think about what you're building, which is a computation graph, in an explicit way, and you benefit from doing that. So in this case, we're just defining the class itself as the layers. If we're going to add dropouts, we'll talk about that in a little bit, the embedded dimension and the contexts, and build the encoder, and then build the decoder. And the setup itself, we want to bind data to this model, and to do it, we have this little setup function that just means we pass data iterators and bind them. And in particular, I'd like you to pay attention to the net loss and net2 group symbols. We'll go over them in a little bit. But that's where you're defining the sort of the terminal symbol or the terminal symbols of your network. So that's where all the computation ends, and that's from where the gradient gets calculated downward. Finally, you just call a method train in our class model. And in particular, train will take your data set, iterate through it, calculate that loss, and propagate the gradient downward. And that group symbol is important because of some work that we're going to do a little bit later on that hopefully we'll get to in time. So how do you train it? Very simple API, just model.fit. I've centralized it because there were some other reasons. In particular, I'm keeping layers, metrics, and optimization parameters in the model. I've taken them out so that they fit in the slide. We ran it through our data, and we had some reasonable first results. So what you're looking at here is the original, the reconstructed, and the embedded layer. And then you're also looking at the mean results for cross-validation of that data. Now, you shouldn't be super surprised. All we're doing is recreating data, right? So if you're recreating data, you should get reasonable results. And what we should be looking at is places where we made mistakes. So at this stage, I haven't really talked about which actual loss function we used, right? We're just talking in general terms. And in particular, if we were looking at autoencoders, if you had binary inputs, pretty traditional cross-entropy. If you had real-valued inputs, mean squared error. But what is a loss function in the context of autoencoding or an autoencoder? It's a similarity measure, right? So you're essentially trying to assess how similar the original input is to your output. And so we, because of the nature of the data that we're dealing with, ended up using cosine distance, right, which is the one right at the bottom. And in particular, I'd want us to concentrate on these things. So not super clear, but on the top and on the left-hand side at the bottom, there are places where there's a mistake in the reconstruction. And so we started looking at what those mistakes were. Why did we make those mistakes? And we ended up finding that the best way to find those mistakes was to do not just a comparison of our training set and the reconstructions, but actually of a transpose of both. So if you think about imagine what a week is, right? A week is a set of things that you could have done and whether you did them or not, right? And counts. So if you take a transpose of those things, then it's all the things that could have happened and the people who did them, right? That transpose ended up being super useful in figuring out how to handle testing for models. Another thing that should be pretty clear from this is that the embedded representation wasn't sparse at all, and we have some intuition. We bring some priors about what we'd like the embedded representation to look like. And so how did we solve these two things? Well, first, we wanted to handle the information loss. As we were testing, so if we use the transpose for testing, we ended up realizing that maybe this feels a little bit like cheating, but why aren't we using the transpose in the loss itself? But before we got there, we actually said, well, what if we add an extra task to the learning that is about finding the rarest thing that happened in that week? So what do I mean by that? You have a week's worth of activity. Some of the things that happened were very popular, and one of the things that happened was really rare. So I can add an extra task to the model, to the training procedure, to try to predict a softmax over it, to try to predict that rarest thing. That should promote the underlying representation to keep that information. So that was our first pass. But our second pass was, wait, why don't we simply just add the transpose, right? We're both trying to predict the weeks and the whole domain and activity structure. And that ended up working really well, but it has an important connotation. Batch size now becomes really important, right? And it becomes really important because batch size will determine how many things end up being in that transpose. right? How many unique things end up being in the transpose. So these were the modifications to our loss. And then to handle that embedded representation, we want to force the representation to have a certain shape, right? So one of the things that you do when you're training a vanilla neural network, a multi-layer perceptron, and you'd like to force the weights to be small, is you add a regularization term, right? A traditional L2 regularization, for example. What does the L2 regularization do? So it forces those individual weights to be smaller, right? To have no one particular weight contribute a lot, right? It's regularizing. You can do exactly the same with the embedded representation and the shape that it should take. So we're adding a sparsity constraint. We're forcing the shape of H or D in this notation, right, of the decoder representation to hold a particular shape. That particular shape ends up mattering a lot, and so we add that sparsity constraint. We'll talk about it in a little bit. So what does that mean? We now modify the model to sort of look like this. We've increased the original dimensions, increased the embedded representation a little bit, and added that sparseness penalty that you can see in the third to last line. So that turns our build stack method into this. So same as before, we enumerate through the layers. We create a fully connected layer, an activation, and now if we're at the last part of the encoder, we add a sparsity penalty. And MXNet provides a nice, handy sparsity penalty. But essentially, you can sort of intuit what the sparsity penalty is by the transformation that happens from the original distribution of the embedded space into the one that you're forcing. And it's right there at the bottom. What results do we get? Significantly improved results, in particular in keeping rare information and also in how our representations looked. But there's a key thing that sort of matters. Figuring out that we could add these extra terms to the loss function to promote characteristics in the embedded representation ended up being a key thing, because you don't just have to, you aren't just allowed to add the terms to promote keeping rare information. You can now promote other characteristics in that embedded representation. And that's sort of what we did. We ended up saying, okay, well, if we have a specific set of attributes that we'd like to model against, we can have beta and the white hat and our prediction of the white hat describe those things. So for example, if I'd like to predict a segment for a particular user, I can make that, since I have that segment for that particular user, I can make that be a loss in all of my terms. And that promotes that embedded representation to then be useful for modeling that particular characteristic, so segment, for example. So if I go from 0 to all the way to that modeling step, I take the raw action data and I pass it through this encoding step that gets a smaller representation, and that smaller representation should allow you to predict that segment. So far, hopefully this makes sense. This isn't where we stopped. We're doing a ton of work. Part of the motivation around this work was, how do we get embeddings such that we can start training sequence networks that don't just understand bits of activity, but activity over time and the relationship between one time unit and another time unit. And that's work that we are currently doing. It's essentially saying, take that day level or week level embedding and pass it through something like a bi-LSTM so that you find a fixed sized vector. In particular, can I create a fixed size vector that represents most of the activity for its particular user? And if I am able to do that, that fixed size vector should be quite useful in downstream modeling tasks. On the lower hand side, we have just the original sequence, and on the top, you'd have the same sequence reversed, right? So you're just trying to predict the sequence itself again. So again, it's an autoencoder, but in this case, it's an LSTM autoencoder. And finally, we'd like to be able to do something slightly different. This is no longer about finding this fixed size representation, but rather trying to find a representation that has certain characteristics, in particular, that has a certain shape, so applying KL divergence to it, so that we can take that representation and corrupt it. And what do we mean by corrupt it? Add noise of the distribution, add noise of the type of distribution that we chose to constrain the representation by, so that in the corruption, we can then use the data set's characteristics without really using any actual data from people. Why would we like to do that? When we're doing aggregate evaluation or aggregate analysis, we still like to distance ourselves as much as we can from the raw user data, just for cleanliness sake. All right, and I've gone quite fast actually, and this is the end of the talk. Hopefully, it was useful and interesting. Thank you. And if you have any questions, feel free to ask.
How did you choose the architecture of the network? Or how did you optimize like the number of layers, the number of neurons, operation functions, so on? Did you follow any specific strategy or something?
Yeah. So the question was, how do we choose the architecture? So we had a lot of information to begin with because we did a fair bit of work on the matrix factorization tests. So that told us about roughly what kinds of sizes of the embedding layer we needed. So we had that bit of information. And then we started with the simplest model that we could. So that's one layer embedded representation and the following layer, right, the decoding layer. It became very quickly apparent that overfitting wasn't a particular problem. So we increased depth fairly quickly until we found that really we were over capacity. There was no need to do it. And after that, we started modifying how particularly the activation functions affect the final representation. And that's where we found most of the gain, actually, and which activation functions we ended up using toward the end.
So you went from number of layers to number of neurons, and then finally optimizing the
First, number of neurons in the center, which we sort of knew because of the initial test that we've done. Then number of layers, increasing almost by 2, by 2, and by 2. Then when we were clearly over capacity, stop adding new layers. And then after that, testing on the activation functions.
Thanks, very interesting talk. You said that in the end you used the raw count to pass to the first layer of the network. Have you tried with the TF-IDF? And it doesn't improve?
It doesn't improve, no. Yeah, we did. We tried a bunch of different pre-processing techniques, both in the matrix factorization step and afterwards. And it didn't give us any meaningful improvement.
I was wondering, when you engineer your loss, first you have to kind of wait till there's huge loss, right? And you said you had alpha and beta factor. Can you give us an intuition how you set those factors over the time?
Yeah, absolutely. So we found for the loss that attaches the transpose, the relationship between that factor and the batch size was really important. And really what you're saying is you're giving importance to how much you'd like to recreate the week itself or the day itself, or the full information in a batch, in a very large batch, which really means how much do I want to understand each action type. And because the action types are quite varied, then we ended up going for the final implementation of this promotes a lot more learning the transpose than the actual weak reconstruction. Does that make sense? Yeah.
Well, you transformed your matrix and your loss function, and you mentioned batch size was really important then. How long did this take to train that?
It takes a couple of days. It doesn't take a lot. We do have, I mean, we're sort of lucky that we have a lot of data. The main constraint there was GPU memory. So if we really wanted, so there's, your batch size, even if you're not doing this kind of work, matters, right? It matters because the first time you do this kind of work, you try to go for the largest batch size that fits in your GPU because that's going to go the fastest, right? And that's not necessarily what you want. In a way, that was a constraint for us. Batch sizes that were very large were a necessity. And time wasn't really the constraint. It was how much of that batch size we could fit into the GPUs.
Could you just explain a bit more about this last slide and why you think that is a good approach?
So there's a significant amount of benefit to understanding the characteristics of a data set independent of where that data set came from, right? And the simple version of this, or not the simple version, but the easy to intuit version is images, right? So if you're training a generative adversarial network, half of that network is a variational autoencoder, right? You're placing a constraint on the embedding space so that it has a certain shape. And then once you know it has a certain shape, you can just either inject noise or create a sample from noise from that distribution, and then create an image. If you do that in the context of actual data, right, data that comes from people generate data, then you get a neat benefit. You keep the characteristics of that data set while being able to really distance yourself, destroy, delete all of that original data. As much as we can, we're trying to find ways to do that. Does that make sense?
So it's abstracting the model.
You're attempting to find mechanics that give you the characteristics so that you can, in all of your training, keep privacy, really. Because remember, these encodings are later used for downstream modeling tasks. Great. Thank you very much.